First, a few reminders. We deal with density functional theory. And in density functional theory, we have to solve self-consistently the Kohn-Sham equation, meaning that if we fix a Kohn-Sham Hamiltonian and solve this equation, we'll find some eigenfunction from which we can construct the charge density, and then plugging the charge density into the Hartree and exchange correlation potential and also energy, we can find the Hamiltonian. Equivalently, one might deal directly with the minimization of the total energy. Here is the electronic part. The nucleus-nucleus interaction part can be added. It is very simple. It was briefly mentioned in the previous talk. So with the kinetic energy, the potential energy, the one created by the nuclei, and then the Hartree and exchange correlation energy that depends on the density. You see in this slide I'm explicitly writing the potential as a sum on atomic contributions, each atom being characterized by a unit cell and a position in the unit cell. How to represent all these quantities, wave functions, densities, potential, etc. We will try to work with Planewave in this presentation. But, and this connects with the previous presentation, there are prerequisites for the Planewave to be used. Indeed, they are very simple functions, but they have an infinite spatial extent. So one cannot use a finite set of plane wave to represent a truly localized system. It would be actually, one might make a Fourier transform to find the decomposition. We would need to have an infinite number of plane waves. So we will directly place ourselves in the context of periodic boundary conditions. We will have some primitive vectors, primitive cell volume, and we will be able to deal with actually quite large cells. Sometimes it's only a few atoms, sometimes we can handle 100, 1000 atoms. That's not a problem. We simply have to rely on a periodic system. Of course, you might say, and this also connects with the previous talk, it's okay for crystalline solid, but what about finite systems, surfaces, defects, polymer, etc.? Well, we will use the supercell technique. A few figures at this level. If we want to deal with a cluster, well, we will have actually it placed inside a cell that we repeat periodically, and as soon as the distance between the cluster here and its image in the neighboring cell is sufficiently large, that's no problem. As mentioned by Sergei, one might need to do a supercell size convergence study and see whether we really have an independence of the property that we compute with respect to the distance between the images. We can deal with a point defect in a bulk solid. As you see, there is an image of the point defect here, and we have to make sure that the images are far apart. Or we deal with a slab in order to simulate a surface. Now let's go to the maths of the plane wave basis set. It's actually all contained in this formula for the wave function. A wave function at point R with wave vector k belonging to some band, but I have not written explicitly the number of the index of the band here, will be a normalization factor and a sum over plane waves. There will be something to be said about this coefficient, and then the plane wave form. Let's introduce this by again completing what Sergei mentioned. We work with a periodic system. We must have the wave vector characterization of the wave functions thanks to Bloch's theorem. Indeed, for a periodic Hamiltonian, this was proven by Bloch in 1928 or something like this, so a long time ago. the wave functions can be characterized by a wave vector or crystal momentum in the Brillouin zone. The Bloch theorem states that if one translates the wave function, the eigenfunction of a periodic Hamiltonian, by some real space lattice of the real space vector of the lattice, we will obtain the original wave function multiplied by a phase factor, a global phase factor. Now, if I decompose the Bloch wave function into some constant, this is not important now, times a phase factor that depends on r times this function u, it can be shown that the u function is actually periodic. It's not affected by a translation. So the normalization, how is it chosen? And this is quite often not described. Well, one might take another standard trick in the literature to introduce the Born-von Karman supercell, which is a supercell of the primitive cell or even the supercell that I am treating. This Born-von Karman supercell will have to be extended up to infinity in the theoretical treatment. It will be a supercell with vector nj rj, with the big number n being n1, n2, n3. And we will require that on the border of this Born-von Karman supercell we have a true boundary condition also for the Bloch wave functions. This allows to normalize the wave function to have one electron in the big Born-von Karman supercell. By plugging this normalization into this formula, also taking into account the n number, the multiplication factor of the Born-von Karman supercell, one can see that the u function that we are really dealing with in numerical computation will have the following normalization when you integrate the square of the modulus of this u wave function over the cell, the primitive cell or the supercell, and divide by the volume of the supercell, one gets 1. So, next step in the treatment with a periodic boundary condition for the plane waves. The definition of the plane wave basis set is done by mentioning what are these G vectors defining the plane wave. Simply, the G vectors are those that fulfill the periodic boundary condition of the primitive cell, Eij Rj equal to 1. And it can be quickly observed that this forms indeed a basis set for all periodic functions in the primitive cell. So we are able to expand any periodic function by summation over all reciprocal space vectors. So these becomes simply coefficients. It's a change of notation. I implicitly consider that this is a function of r, and this quantity is a function of the wave vector in reciprocal space. It's a number, and this number multiply the plane wave. So plugging this formula into the previous expression for the Bloch wave function, we obtain the following expansion in a function of the plane wave with coefficients that multiply Eik plus j r. The k comes from the previous equation. Here you had this Eikr multiplying the real space periodic part of the Bloch wave function. Oops. Okay, But we don't want to deal with an infinite set of plane waves with our computer. We need to make an approximation. There is a natural way for plane wave to select the correct or the best plane wave set. Indeed, when you consider the kinetic energy of a plane wave, which is like this in the case of the block function, not simply its periodic part, it can be seen that each plane wave, when this operator is applied, becomes simply itself multiplied by k plus j squared divided by 2. So the kinetic energy, well, actually plane waves are eigenstates of the kinetic energy operator with such eigen energy. And actually the coefficients UKG for the lowest eigenvectors, the one in the valence states or the lowest conduction bands, decay fast with the kinetic energy. So naturally we will select a finite set of plane waves by imposing a cutoff energy, E cut. We will select only those plane waves that satisfy this inequality. We fix the E cut, and the j here must be such that k plus j squared divided by 2 is smaller than the E cut. Note that in the reciprocal space, this inequality makes a constraint on the norm of the k plus g vector, which actually defines a sphere in reciprocal space. So one speaks of the plane wave sphere. Of course, these g vectors satisfying this condition are vectors in the reciprocal space lattice, so it's a discrete set of vectors in the reciprocal space, and so we will only work with the reciprocal space vector j that are inside the sphere delimited by k plus g norm being giving this kinetic energy lower than E cut. Actually, I might show you immediately an illustration, in a two-dimensional illustration of this fact. I will come back later to my earlier slides. We can plot as a function of the cutoff energy, here where we'll take the square root in order to go back to the length in reciprocal space. In two-dimensional, we will not have a sphere but a circle, and you see I'm selecting, thanks to these different circles, all the points, discrete points that form a reciprocal lattice here shifted by the k vector. I'm selecting a finite number of plane waves. If I take this circle, I'm selecting 1, 2, 3, 4 plane waves. If I increase the cutoff energy, I will include in the circle also these 8 plane waves. I'm going to 12 plane waves, then 16, then 24, etc. Typically for small cell system like silicon with 2 atoms per unit cell, we will deal with 300 plane waves when we will use pseudopotential, to give you an idea. Okay, so we know what is the plane wave basis set that we choose to represent the wave function, and it's quite simple. Numerically, we will have to represent a wave function by 300 numbers for the case of silicon wave functions. How shall we represent the density and the potential? These are other quantities to be represented. Well, it's also very simple with plane waves, because every such function is also a periodic function, and we will use, like for wave function, such an expansion with plane wave. Here, these are truly periodic functions. Block functions are shifted k-point periodic functions. And the coefficient of the representation of the function can be found by this formula. So actually we will have a Fourier transform between real space and reciprocal space. Now let's see first what is the connection between a density and the potential. It's given by the Poisson equation. Well, this integral equation changing from the density to the potential correspond in reciprocal space, in real space to this Laplacian, which is equal to minus 4 pi times n. Going to Fourier coefficients, we have simply this becoming g square VR3 is equal to 4 pi times the density. And then we divide by g squared and obtain the R3 potential from the knowledge of the density. You see, in reciprocal space, it's a very easy thing to do. As mentioned previously by Sergei, there is a problem with the g equal to 0 component, which connects to the homogeneous charge density, the average of the charge density. If this n of g equal to 0 do not vanish, then the R3 potential diverge. But in practice, we always deal with neutral charge cells because, well, at the level of a globally neutral system, we have a correct compensation between the electrons and the charged nuclei. But if we go to charge cells, then we have to add by hand a compensating background charge. Now, what is the connection between the density and the wave function? It's also quite simple, but actually we will treat it not in reciprocal space, but in real space, as I will explain. Because indeed the most natural formula to obtain the density of some eigenstate of band n at eigenvector k is simply by combining the complex conjugate of this function with itself. Now, one might indeed consider that the wave function in real space is obtained from plane waves, both the complex conjugate and the function itself. We combine these two expressions and we find that actually the two plane wave factors combine to give another plane wave. That's nice. But however, the g prime coming from the first wave function and the g coming from the second wave function can combine to go outside of the initial plane wave sphere. Actually, from this k plus j, from some wave function, and this k plus g prime from the other wave function, we make the difference and obtain a vector that is outside of this original plane wave sphere. But that's not a problem. Indeed, for densities, we consider a sphere plane wave that is of double radius with respect to the wave function. And still, it's an exact expansion of the density. So we know how to go from the wave function to the density, from the density to the potential. But are we happy with this function? You see there is a double sum over the plane waves. Double sum means 300 plane waves times 300 plane waves. It's 90,000 calculations to be done. While here, we were simply dealing with something, with a simple multiplication in real space. And actually, we can use what is called a discrete Fourier transform, and it's a key point in all plane wave-based implementation of density functional theory. We will have a dual representation, and we will quickly switch between the real space and the reciprocal space. Well, I will not enter into the detail of the algorithm that allows to go from real to reciprocal space. This has been developed by mathematicians. It's especially efficient. It's not scaling as the square of the reciprocal, as the product between the reciprocal space basis set and the number of real point space that we want to compute. It's something much more clever that scales as a linear linearly with respect to such numbers times the logarithm of these numbers. So we switch easily from the reciprocal lattice with these two spheres to the real lattice, which is actually a sampling of the original primitive cell. Okay, at this stage, we will not only evaluate the density in real space like this, but also the exchange correlation quantities, which I will not detail here. So we are able to build a full electronic part of the total energy, knowing the wave function. This is quite simple and quite easy to implement compared to any other type of implementation. However, there is a problem with plane waves. Indeed, the Fourier transform theory teaches that details in real space are described if their characteristic length is larger than the inverse of the largest wave vector norm, roughly speaking. So if we have very small characteristic length, we will need a very large number of plane wave, or sphere in reciprocal space will be very large because of this inverse characteristic. On the other hand, we have the nice feature that the quality of a plane wave basis set can be systematically increased by increasing the cutoff energy, which is a very nice feature of the plane wave basis set, not very often found by other basis sets. So if we directly plug in the Coulomb potential created by a nucleus into a plane wave code, it will succeed to obtain the right result, but sometimes with a huge number of plane waves. I was speaking of 300 plane waves for silicon with pseudopotential. Actually, to treat silicon without pseudopotential, I think one would need 1 million plane waves of something like this. So it's a problem. And the localized feature come not only from to describe the core orbitals, the 1s orbitals of silicon, but also all the other orbitals have oscillations close to the nucleus. And that's what we will treat pseudopotential. In general, pseudopotentialization will eliminate the undesirable small wavelength feature. So this wavelength feature will be later seen. I'm showing you first the typical convergence study that one has to do with plane waves. You see, as a function of the cutoff energy for bulk silicon, one can plot the total energy here in R3 and observe that it will slowly tend to a well-defined answer, something like 1 milli-R3 per atom or less is often requested for a calculation to be considered converged. This I have already shown you. Yes, the number of plane waves that is included when we increase the cutoff energy is clearly discontinuous. You see, one goes from 4 plane waves to 12 plane waves to 16 to 24, and this depends on the size of the sphere. It happens that there are some subtleties linked to this discrete increase of plane wave. For example, if one does not take care sufficiently and do a quite rough calculation for the total energy, one might find a behavior of the energy, total energy, as a function of the lattice parameter, like this one. Instead of being a smooth curve with a very nicely defined energy minimum, we have a rugged curve. Well, these things here correspond to a sudden change of the number of plane waves. The pressure might also have a very strange behavior. This is usually taken into account in modern total energy code. One introduces a so-called smearing function that will actually smoothly introduce new plane waves inside the basis set, and the curve then is very smooth. So this was a well, the most important thing to know about the plane wave basis set, I will now introduce the pseudopotentials and their different flavors. Let's first make a distinction between core and valence electrons. We know from the ordinary chemistry that only a fraction of the electrons really takes part in the forming of the bonds. And by contrast, the core electrons are those who occupy orbitals that are the same in the atomic environment or in the bonding environment. But this is very qualitative. How to define it in a better way? Well, it's not easy, and actually can be done in a somehow arbitrary way. It will depend on the precision that we want. Let's suppose that we make such a distinction and select, let's say for silicon, the 1s, 2s and 2p orbitals as being in the core, and the 3s and 3p orbitals being in the valence. Then our formula for the density is very easy to split. Indeed, it's a simple sum over the occupied states, and we will consider differently the bands that are related to the 1s, 2s and 2p states, and sum them separately from the bands that are valence-like. So it's the density of the core orbitals plus the density of the valence orbital, and we can make the frozen core approximation and suppose that the 1s, 2s and 2p orbitals are actually frozen and do not change going from the atom to the solid environment. This is easy. I mentioned that this separation is not easily defined. When we work with some elements, especially those in the higher part of the periodic table, the covalence partitioning for normal precisions, normal target accuracy, is quite obvious. For example, if we take the fluorine atom with this configuration, 1s2, 2s2, 2p5, this 1s state in energy is at 1 kilo electron volt down. The ionization potential is on the order of 1 kilo electron volt, while the 2s and 2p states have an ionization potential in the range 10 to 100 electron volt. Also at the level of the spatial localization, the 1s state in fluorine is much more localized than the 2s and 2p states, and in agreement with the chemical intuition we will treat these as valence and this one as core. But if one takes titanium with this atomic configuration, the chemical intuition says that the 4s and 3d states will have to be treated as valence. We are sure that the 1s, 2s and 2p also will be as treated with as cores, but the ionization potential of the 3p state is 100 electron volt, while the ionization potential of the 4s is 43 electron volt. You see that there is only a factor of 2, and also there is an overlap in localization region between the 3p and the 4s. So the possible change of occupation of the 4s state might yield a change in the potential that is felt by the 3p states and the rearrangement of the 3p states. So we can actually work in both cases. Either consider we have a small core for the titanium atom and thus a very large number of valence or explicitly treated valence electron, or use the following splitting: a large core and a small number of valence electrons. This will actually be fine for the titanium metal, because in the metal the 4 electrons will roughly occupy these 4s and 3d states. But if you take barium titanate with the oxygen pumping the electrons from titanium, here we will have somehow a 4s 0, 3d 0 state, and the 3p and 3s orbitals will be rearranged. You cannot get correctly barium titanate by using this separation. It's even worse when you go to an atom in the 4f region, rare earth or even the actinides. There the separation is really badly defined. The secure side will be to include a very large number of electrons as valence, which increase the computational cost, as also it will have a smaller size of feature to be described. So it will not be easy. It's a compromise between accuracy and computational cost. Now, this was for the density. What about the total energy? Let's take explicitly our expression for the Kohn-Sham energy, kinetic density in the potential created by the nuclei. This is the Hartree, and this is the exchange correlation. This part is easily split also between the core contribution and the valence contribution, because it's simply additive. This part, well, the density is split between the core and the valence. This one is quadratic in the density. We will have not only the core-core interaction and the valence-valence interaction, but also the cross product, the valence-core interaction. And then for the exchange correlation functional, things are a bit more delicate. At this stage, I simply write n core plus n val. So we have this line completely defined and related with the core. This one completely related to the valence, while the cross products are present in the third line. It happens that we will be able to treat this term very easily by actually plugging it inside this one. You note n val is present here, like here, and then the Vx will be combined with this density of the core screened by the Coulomb. Well, the Coulomb potential created by the n core. This is the natural introduction of what is called an ion. Indeed, the potential created from such ion is the Coulomb potential of the nucleus plus the screening due to the core electrons inside this formula. So actually, we naturally see this apparition of ionic potential, and we can write the total energy as being due to different terms, the valence contribution, which is written here, kinetic, ionic, Hartree, and then the core and valence exchange correlation. Here there is a sum of core-only contributions, and actually the final formula is obtained by also taking into account the fact that we will change our bare nucleus charge to a screen ionic charge, and actually we have an interaction between ionic entities replacing the bare nuclei. Okay, from the previous construction, we have succeeded to treat easily the core orbitals, but still valence orbitals must be orthogonal to core orbitals, which means that they will oscillate. We will have a slope at nucleus, and this means that it will be quite difficult to describe with plane waves. Pseudopotentials will try to remove completely the core orbitals present from the simulation. No orthogonality will be needed. Of course, for those who know the characteristic of the one-dimensional radial function, there is a problem with the number of nodes that are present for the higher lying function. So it's a really strong modification of the system. But the construction that I will show you will confine the strong changes in a so-called cutoff radius. So it's not a cutoff energy that was present for the plane wave basis set, but a cutoff radius. We will go from the upper equation here to another equation where we replace the potential created by the bare nucleus by a pseudopotential. We replace the wave function, the all electron so-called wave function, by a pseudo wave function. So what is left? We replace one equation by another equation. Well, we have to do this in a clever way. The possible set of conditions to replace this equation by this pseudo equation, which was introduced in 1979 and is called norm-conserving pseudopotential, is to impose first, well, this is obvious, kind of the energy, the eigenenergy, is exactly the same in the true system and in the pseudo system. Second condition, the all electron wave function and the pseudo wave function must be equal beyond some cutoff radius. And then another constraint, we require that inside the cutoff radius we have the same charge from the pseudo and from the original wave functions. This is related to the idea of a norm of the wave function, and that's why it's called norm-conserving pseudopotential. And moreover, we want to do this for the lowest angular momentum channels, S, P, sometimes D, and F. Okay, this is not the only possible set of constraints, yes. There are generalizations that I will, according to the time that I'm left with, describe ultrasoft pseudopotential and projector-augmented plane waves. This is an illustration of a norm-conserving pseudopotential for silicon. The 3s radial wave function, so a valence state, initially has this behavior. The green followed by the blue here. And we will replace it by this function. You see, it is smooth. It will be easy to describe with plane waves, unlike the green one. It is actually, when squared and integrated, giving the same integral when evaluated from here to there. And then beyond this point, we have exactly the same wave function. The 3s radial wave function in the new, for the new wave function is obtained when one considers this potential. You see here is the radial distance. The initial Coulomb potential, the attracting one created by the valence charge, was like this. And we strongly modify the potential, but only below this radius, inside a sphere around the nucleus. As you might notice, there is a different potential for the p electrons and another potential for the d electron. How is it possible, actually? Well, a pseudopotential is a more general object than a normal potential. A normal potential is a so-called local operator. But actually we can rely on a more general form. We want simply an object that transforms a wave function to another function, and this is achieved by doing that kind of mathematical operation. We define a linear and Hermitian operator, and a linear and Hermitian operator is characterized by a kernel that, integrated on R prime with the wave function, deliver a function evaluated at R. The kernel might have, broadly speaking, of course, a local part, but also have a non-local part. In the usual potential created by the nucleus, only the local part is present. Of course, we want this object to be spherically symmetric. It is to replace the atom, and the atom was spherically symmetric. We want it to be spherically symmetric. The local part can only depend on the distance with respect to the origin. But the non-local part can be expanded in spherical harmonics, and it happens that the general formula for this is given here. You recognize spherical harmonics here, and then the V present here depends on distances with respect to the original, and also depend on the L. So it can be different for S, P, and D orbitals. There are actually two types of such functions that have been introduced in the past. Either the semi-local pseudopotential, where the VL of R prime was a simple VL of R delta R minus R prime, or a separable pseudopotential in which we have something a bit more complex, but still we have a dependence on L. And actually there is a canonical way to go from this form to that form that I will not explain. So what I have shown you is the VL of R that was present in the semi-local pseudopotential case for the S electron, for the P electron, and for the D electrons in this pseudopotential. Okay, now one can further elaborate these concepts. These actually are very well established concepts, but these were introduced something like 3 decades ago. So what people work usually with are ultra-soft pseudopotential or PAW, although for some application norm-conserving pseudopotential are still used. They are much easier to implement than the PAW, for example. So the ideas, ultra-soft pseudopotentials comes from a criticism of norm-conserving pseudopotential. Indeed, when it comes to treat oxygen with the 2p orbitals, or iron with the 3d orbitals, or the 4f rare earth, one typically sees something like this. The continuous line is the oxygen 2p orbital. The dotted line is the best that one can achieve in the norm-conserving case, where you see, because there is no node present, the smoothing is nearly not possible. You see the peak of this wave function is at 0.2 or, well, 25 atomic unit, while for silicon the peak was around 1.5 in atomic unit. So you might understand that the number of plane waves to treat oxygen in norm-conserving pseudopotential is simply huge. And the ultra-soft will actually replace this function by this one. Okay, it's the same beyond some cutoff radius, but it's completely different inside the cutoff radius. What was done? Well, something quite clever. The normalization has been changed, but in a way to enforce correct scattering properties. Somehow, if electrons hit this pseudopotential, ultra-soft pseudopotential, they will act like if it were true potential, so the diffusion will be correct. And also, one has to introduce charge density correction. Such construction actually can be obtained as a particular case of the PAW construction, so I will not detail the USPP construction here, I will detail the PAW. But for selected elements like oxygen, iron, etc., one reduces the size of the plane wave basis set by a factor of 3, 4, 5, with even a bigger saving in computing time. The projector-augmented wave approach, introduced in '94, has the following idea. The true wave function, all electron, will be connected uniquely to the auxiliary wave function, actually a soft pseudopotential, by a linear transformation. It is rigorous. So one can indeed make always a connection back to all electron wave function, which the USPP, ultra-soft pseudopotential construct, cannot easily do. They have things in common. In both cases, we will change the Schrödinger equation or the Kohn-Sham equation to an equation in which there is an overlap operator, which is a bit similar to the case where people treat wave function with localized orbital. And also the charge density of each state has to be corrected for the missing norm. The math, it's a bit long, so I will see what I can explain in the few minutes that are left. As I say, the true wave function is connected with well-behaving pseudo-wave function thanks to a linear transformation. The physical quantities, like this expectation value, will be computed in the pseudo-representation with this psi tilde, the A tilde, the psi tilde, and the A tilde is defined by the T emission conjugate AT. We will have a variational principle for the total energy that can be transformed to the pseudo space and give an equivalent to the Kohn-Sham equation, where, just to give you a flavor, the second, the right-hand side member becomes epsilon T dagger T. So this is the S overlap matrix that appears naturally. The transformation operator will be 1 plus a sum of atomic projectors or atomic operators. And these atomic operators will be defined by the following transformation. One takes partial waves, solution of the Schrödinger equation for the isolated atom in the full potential. One takes also pseudo-partial waves that will replace these partial waves. You see, smoother inside the cutoff. And the trick is that we define S such that 1 plus SR applied on the pseudo wave function, or pseudo partial wave, give the full partial wave. So we have defined a way to go from the pseudo to the all electron spaces. This is a graphical illustration of the PAW technique. So let's see what we have done until now. We have defined a transformation. Actually, the way we will have the presence of some wave, all electron wave function and partial wave and pseudo partial wave is governed by the application of a projector that I will not deal with. It has to be constructed from the theory. So you see that the full wave function is the pseudo wave function plus a sum over the atomic sphere of something that is all electron-like minus something that is pseudo-like. So the full wave function, yellow means it is smooth, blue it is very peaked, very hard, oscillating, etc., will be a plane wave part here, plus an all-electron spherical part, hard but only present in this sphere, minus the pseudo-partial waves. So at the end we obtain the correct result. One can do the transformation not only for the wave function, but for the density, for the total energy. And we will have globally always formulas that give a smooth contribution into the whole space, plus a sum over spheres of a difference between the all electron and pseudo contribution for the density as well as for the energy. There are some approximations that are done. So although it is possible to have a perfect mapping between the all electron case and the PAW case, we can see the following approximation. We of course treat the core electrons with the frozen core approximation. We will have a finite plane wave basis set, but we can check the convergence. And also the partial wave expansion inside the sphere will be truncated. Usually only one or two partial waves for each atom, and each angular momentum channel will be taken into account, which means that the constraint that I have not described, we should have kind of a completeness relationship inside the sphere, is not fulfilled, but they are compensating quantities so that this method even works with one or two partial waves inside the spheres. Okay, what are the advantages of the plane wave plus pseudopotential or the PAW method? Okay, thank you. Well, the basis set that we have introduced, plane waves, does not depend on the atomic coordinates. This means that we will have an easy computation of forces as numerically exact derivative of the total energy with respect to atomic coordinates. We can avoid so-called Poulet forces. Actually, this works also at the higher level when computing phonons using density functional perturbation theory, so direct computation of phonons. We will have no complications related to the dependence of the basis set on the position of the atom. So we will have easy structural optimization or molecular dynamics, and also the Karp-Agnello technique is easily implemented. Another advantage is that there is a systematic way to complete the basis set. We simply tune the cutoff energy and we obtain a better numerical solution of the system. Now, for plane wave pseudopotential, the norm-conserving pseudopotential, the implementation is moreover quite simple. And there are actually many properties in all the codes that I can think about that have norm-conserving as well as PAW. So many properties are not implemented in PAW, but are implemented in norm-conserving. Well, with time it tends to be less and less, but still to my knowledge, for example, there is no direct third derivative of the total energy computed in the FPT using PAW, while it's implemented with pseudopotential, norm-conserving pseudopotential. For plane wave PAW, it can be a numerically accurate implementation of DFT, including properties related to the cores. And it's usually faster than plane wave pseudopotential norm-conserving. However, it cannot yield an order n implementation. It is also constrained by the periodic boundary condition, so it does not treat efficiently finite system, and the higher lying states, very high in energy, cannot be trusted. But let's say for 99 of the applications nowadays, plane wave PAW is really a method of choice. I have here a list of generators of that is not complete, but for norm-conserving pseudo, USPP, PAW, you can have a look on these. Implementations are also numerous, norm-conserving, USPP, PAW. And this is, to give you a flavor, a pseudopotential table that is found on the web. Here you have simply to click on one of these green squares and you will obtain a pseudopotential. This table has bin thoroughly tested. You will hear more tomorrow in the validation talk by Cotenir or Le Jagere, I think. The delta factor is 0.4 MeV. You will hear what is the delta factor. I wanted to say a few things about this, but I'm a bit short, and in any case it will be covered tomorrow. What I want nevertheless to say is that nowadays, if we compare the results with all electron pseudopotentials of different codes, which lies in this delta factor measure below 1 and typically in the order of 0.5. The agreement between different implementations of all electron is on the order of 0.5, and the agreement between PAW and all electron that is presented here is slightly higher but not much. So basically PAW is doing a very great job even compared with all electron. And actually it's even possible to get good number for norm-conserving pseudopotential, and it's improved with the year. Actually, well, here I had another table, but that was for norm-conserving. It's quite really decent with respect to all electron data. So this is a summary of the key points. Thank you for your attention.